So in this video, I'll be solving problem 2.21, which states, find the potential inside and outside a uniformly charged solid sphere whose radius is r and whose total charge is q. Use infinity as your reference point. Compute the gradient of v in each region and check that it yields the correct field. Sketch v of r. So I'm going to begin this problem by defining the electric field outside the sphere. And we're going to be using Gauss's law to solve for the electric field. And I'm going to draw that surface in blue here. And I want to define my surface so that it's also centered about the origin. And I'm drawing it as a sphere so we can enact what's called the argument of symmetry. And this argument of symmetry allows us to say that the electric field, no matter where you draw it on our Gaussian sphere, it will always be pointed radially outward. And you can prove this to yourself by choosing 2 points. Well, by first choosing a point, you want to find the electric field, of course, and you could choose 2 points that are symmetric about this axis that connects the electric field point and the point that's closest. So there's an electric field due to this point on the left, and there's some electric field pointed due to the field on the right. And both of these fields have some radial component that is contributing, but they also have some angular component that is sort of throwing it off of being pointed radially outward. However, this angular component on each of the vectors, because they're symmetric, will cancel. And this is true if you choose any 2 points on the surface, as long as they're symmetric about, remember, the axis that we drew originally. This argument of symmetry is incredibly powerful because it allows us to say that the electric field is equal to the magnitude of the electric field in the r hat direction. And I'm also going to define our EDA vector here. Which is equal to the magnitude of dA r hat, because whenever you define your Gaussian surface to be a sphere, the dA vector will always point radially outward no matter what point you choose on your Gaussian sphere. So now let's go back to the integral. And our Q enclosed here is our total charge Q, which is quite simple. So we plug that in there. R hat dot R hat is just 1, so I'm going to get rid of those for simplicity's sake. And the electric field is a constant, so I'm going to pull that out of the integral. And the integral of dA is, of course, just A. So I can define our electric field magnitude to be such. And surface area, of course, is 4 pi r squared, where little r is the radius of our Gaussian sphere. Remember from our argument of symmetry, we can turn the magnitude of the electric field easily into a vector by simply adding this r hat and turning it into a vector. So now let's solve for inside. Again, we're going to use Gauss' law. So I'm going to draw another sphere so that we can enact the same argument of symmetry. And there's still some Q enclosed here because it's a solid sphere. And remember, we can enact this argument of symmetry where these 2 points are on, don't get it confused, these 2 points are on the charged sphere, not our Gaussian sphere. And they enact this definition of the electric field where it's always pointed radially outward. Again, dA is the same because we define our Gaussian surface to be a sphere. So I'm going to skip a couple steps here. I'm just going to jump straight to after we've pulled everything out of the integral and integrated dA, where E times A is equal to Q enclosed. So our Q enclosed has changed here. We're looking at a smaller volume. And so the total charge Q is no longer what we're looking at for our Q enclosed. How do we solve for this Q enclosed? Well, we know that the sphere is uniformly charged, so I can say that Q is proportional to the volume, and volume in any case is proportional to R cubed. So I can create this ratio between this Q that's enclosed in our smaller sphere, this dotted line, and the total charge Q that is enclosed within this the total uniformly charged sphere. And that's equal to the ratio of their radii cubed because of these two proportionalities. So we can solve for QR. So let's go back to solving for the electric field now that we've defined our Q enclosed. That Q stays along, and we have the epsilon naught, and what else? We have this A, of course, so 4 pi r squared, where again little r is the radius of our Gaussian sphere. And I'm forgetting this proportionality between the two radii cubed. So if we solve for E, you'll see that the little r's will cancel. And thus our electric field magnitude is equal to Q over epsilon naught over 4 pi multiplied by little r over r cubed. Because of the symmetry argument, we can turn this into a vector. So now we have defined the electric field inside and outside the sphere. All right, so we're ready for the next step to solve for the potential. And I've moved our electric fields up here, and I've also included the general equation we're going to be using to solve for the potential. Let's start with outside the sphere. And I'm going to kind of rewrite the general equation. And in this case, we can exclusively use E out, and I'll explain that actually. So if we define this position vector R to be outside the sphere, and we want to be smart about where we put the reference point vector. Of course, this goes out to infinity. We define this position vector so that we can define dl, the path over which we're taking the integral, to only change in the r hat direction. Notice, like I drew this arrow here to sort of exemplify that it's only going to be changing in this dr direction when we're going from infinity to this distance r. So let's rewrite the integral now in scalar form, where we're going in from infinity to R, and E out. Remember, r hat dot r hat is 1. So I can write the integral as such. So the constants come out, of course. And the integral of 1 over r squared is 1 over r, negative 1 over r. So this negative cancels up front, and evaluated from infinity to r. Thus our electric field, or sorry, not our electric field. Have I been saying that? Our electric potential is equal to Q over epsilon naught, 1 over 4 pi r. Now let's do inside the sphere. Again, I'm going to rewrite the general equation, vector form. And we're not just using E out in this case. If I put my position vector, I'm going to keep that there. If I put my position vector somewhere inside the sphere, and I put my reference point out to infinity, dl is still only changing in the r hat direction, of course, but we're going to cross this boundary at some point. So I have to split this into 2 integrals when I turn it into the scalar form. And that's going to look like this. So we have negative from infinity, and sorry, we hit this boundary at radius r. So I'm going to say from infinity to value r, we're going to use the electric field outside, Q over epsilon naught 4 pi r squared. Remember, r hat dot r hat is 1, save dr. And then our second integral is going to go from r to little r. And we're going to use the electric field inside the sphere for this piece of the integral. So now we're ready to solve. If you notice this first part, that is exactly the same as we just solved, except the little r is changed to a big R. So I'm just going to quote what we already solved. Let's solve this section of the integral. Let's pull the constants out. Integral of r dr is 1/2 r squared, evaluated from big R to little r. So in this next step, I'm going to start factoring out some constants. We've got a 1 over r, and I'm going to pull out this 1/2 too, so we can work with whole numbers within the parentheses here. So this first term turns into a 2, and we still have a 1 over big R squared left over. Now let's evaluate our bounds. Now within the parentheses here, we have 2 minus r squared over big R squared. Negative 1 over r squared times negative r squared is just plus 1. So we can define our potential inside to be equal to the following. So now we've defined both of our potentials inside and outside the sphere. I wanted to point out in the last clip, I kept drawing these, the dl vector this way. That's incorrect. The dl vector always points really outward, like I defined it too. Why I was drawing it backwards is because the path we're taking goes from infinity to our reference point r. That's taken care of by our bounds. However, the dl vector, I want to make sure that's clear that it's always pointed radially outward. Fantastic. So we've solved for our v outside and our v inside. So now we're ready to check. And we're able to check this because the electric field is equal to the negative gradients of our potential. So let's do this for outside the sphere. We'll bring over our two equations that we need. So if we take the negative gradient of our potential here, we're going to take the partial derivative with respect to r in the of v, so that would be q over epsilon naught 4 pi 1 over r in the r hat direction. And usually we would take some other partial derivatives in the angular direction. However, there's no angles in our potential, so we don't have to worry about that. Let's take our partial derivative. The constants come out. Forgot a negative there. Oops. The partial derivative of 1 over r is negative 1 over r squared, so that will turn to a positive in this next step, and in the r hat direction. And theoretically, that should be equal to the outside of our electric field. Now, by observation, those are the same. So I would say that is checked. Now let's check inside. Again, I'm going to grab these two equations that we need. And we're going to do the same thing. We're going to take the negative gradient of the potential. So the partial derivative with respect to r. And let's rewrite the potential here. So the constants come out, just like before. And we're only really taking the partial derivative of this piece. So when we take the partial derivative of 3 is 0. And then when we take the partial derivative of negative r squared over big R squared, we get, well, first of all, this negative in here will cancel with the negative here. So turning that to a positive, multiplied by 2r over big R squared. These 2's will cancel. So we're left with the following. Dang it. I forgot to put the r hat here. When we take the partial derivative, when we take the gradient, we're not only taking the partial derivative, we're taking the partial derivative with respect to r and saying that's in the r hat direction. So, forgot to add this r hat here, but it is there. R hat. And this should be equal to the electric field of the inside, theoretically, so let's observe. Bravo. Checked. Alright, so we're ready to move on to the last part of this problem and sketch the electric field. So we have we have R on the x-axis and V of R on the y-axis. And to get an understanding of the shape of this curve, we can look at the proportionalities. So V inside is proportional by negative R squared. And V outside is proportional by 1 over R. So this is going to be a downwards facing parabola, and this is going to be like a decaying function. We understand the shape of these curves, but where will these points meet? We know that boundary of which they change is at R. So I'm going to evaluate the V out at R and V in at R. I'm going to evaluate these, and they should be equal based off of just the definition of the potential, but let's evaluate it to make sure so we can graph that value on the y-axis. So for V out, we have Q over epsilon naught 4 pi, and then we can just plug in the 1 over big R there. And V in, evaluated at big R. A little bit more work, but I know we can do it. Let's see, we got big R squared over big R squared. That is just 1. This whole portion turns to a 2. So we're going to cancel that 2 on the top, that 2 on the bottom. And we are left with Q over epsilon naught 4 pi 1 over R. Perfect. They are equal just as I predicted. Alright, so let's put this point somewhere on the y-axis. Let's put it here. Why not? And this point is equal to what we just evaluated. Just point on the y-axis to be clear. Remember, we have our downwards facing parabola first, so I'm going to draw that. Downwards facing parabola. And then we have where they meet here, at the point at which we evaluated. And then we have the decaying function to follow the rest of the outside of the sphere. So this is outside, and this is inside. There you are. We got our potentials graph sketched out. And that is our problem solved. Thank you.